Welcome to 6502 Assembly Language Programming. My intent in this video is to give you an overview of how computers work from an assembly language programmer's perspective. If you already have a good understanding of how computers work, then feel free to skip this video. Otherwise, strap yourself in and we'll have a quick look at how computers work. Computers consist of components that fall into three categories: the CPU, or central processing unit, memory, and input-output devices. As the name implies, the CPU, the central processing unit, is where processing, aka computation, takes place. Memory has two principal uses. One, to store the code that the CPU runs, and two, to store data that the CPU code requires to do its job. To be useful, computers must interact with the outside world in some way, and that's what input-output, or I/O, devices are for. I encourage you to think of the CPU in this way. The CPU is a device that executes instructions and has registers. Each type of CPU has a particular and well-defined set of instructions that it knows how to execute. As an assembly language programmer, you'll be having a lot to do with registers. Most of the instructions affect registers, and you'll spend a lot of time with them. Here is a day in the life of a CPU. Read the next instruction, decode the instruction, execute the instruction, repeat. This is what computers do, and it's important to know that there's no step in here that asks, does the instruction make any sense? Do I like the instruction? Is it going to be useful? Computers are very literal. They consist of electronic circuits that only know how to execute instructions. Computer instructions perform very simple operations, like loading a number into a register or adding the number to the value in a register. In the following example code, the following operations take place. The LDA instruction loads the contents of memory location $80 into the accumulator, or A, register. The ADC instruction adds the contents of memory location $81 to the value in the A register and updates the A register with the results. The STA instruction stores the updated value from the A register to location $82. What's up with the dollar signs? Those signify that the numbers are base 16, otherwise called hexadecimal, or simply hex. We'll discuss this in the next slide. This table is intended to illustrate why we use hexadecimal. It's showing the same number, actually three numbers, in all three forms that we're going to consider: decimal, binary, and hexadecimal. The first number is 65,281 decimal, which equates to that long string of binary digits, and the hexadecimal number FF01. Now, the thing to note about this is that the natural representation for a computer is binary. That's what it works with. But binary is quite awkward for humans. I mean, that long string of zeros and ones just is not easily readable. And certainly, if you're going to read the number out loud to another person, it would be very error-prone. The good thing about hexadecimal is that it's a very compact representation, and you can easily read the numbers. Moreover, the digits of a hexadecimal number map quite readily to the binary digits. For instance, the F of the FF01, the first F, maps to the upper 4 binary digits. In contrast, there is no easy mapping for the digits of the decimal number to the binary. So these are the reasons why we tend to use hexadecimal. Let's talk about memory types. There are two fundamental kinds of memory: primary and secondary. Primary memory is directly addressable by the CPU, whereas data in secondary memory must be read into primary memory before the CPU can work with it. Think of primary memory as a sequential list of locations, each of which has an address and some contents. In the list below, you'll see that address $80 contains the value $48. Now there are two basic types of primary memory: RAM and ROM. RAM, read-write memory, can be used for program storage and is also used as scratchpad area for the CPU to work with. ROM, or read-only memory, is generally used for program storage. Secondary memory is generally used for longer-term memory of data than primary memory. It's much slower than primary memory. And by much slower, I mean an order of magnitude slower. Data in secondary memory must be read into primary memory before the CPU can use it for computation. Usually, data is read into primary memory in chunks, where the size of the chunk is determined by the kind of memory device. And a very common kind of operation is to read data into primary memory, update the data, and then write it back to secondary memory. To be useful, the computer must receive input from the outside world and provide some output. Examples of input devices include keyboards, mice, joysticks, or network connections. In saying network connections, I really mean other computers, because that's what we're going to on the network. And examples of output devices include monitors, printers, speakers, and once again, network connections connecting to other computers. Thank you for listening to this very brief description of how computers work. I do hope it helps you in understanding the material that you'll find later in the course. Have a great day.